String theory. Yeah, I know. Even for physicists, that word can be a little intimidating. But what if I told you the core idea? The real heart of it isn't that complicated at all. What if you could get it just by understanding a simple, beautiful analogy? So let's dive in, because we're going to break this all down using a really powerful idea from one of the giants of the field, Edward Witten. See, here's the key. Witten's idea is that physics, kind of like history, has these rhymes. You find these little echoes, these similar patterns and mathematical structures popping up in places you'd never expect. And if we can just spot one of those rhymes, we can make this incredible leap from the physics we all know and love into the mind-bending world of strings.
And look, we're not just doing this for fun, right? The puzzle we're trying to solve here is, well, it's the big one. It's the massive conflict between Einstein's general relativity, the theory of the very big, and quantum mechanics, the theory of the very small. For almost a century, these two theories have just refused to play nicely. This rhyme, it might just be the thing that finally brings them together.
Okay, so to get this rhyme, we've got to start with the first verse, the world of particles. We're going to take a look at something physicists have been using for decades, particle interactions, but we're going to look at it from a totally new, kind of weird angle.
So usually when physicists want to figure out what happens when two particles smash into each other, they draw these little pictures called Feynman diagrams. You can basically think of them as little cartoons of reality. Particles are just simple, one-dimensional lines moving through time, and whenever they interact, bam, the lines meet at a sharp point called a vertex.
Now, here comes the first part of the rhyme. This is so cool. Witten pointed out that if you sit down and write the equations for a super simple toy model of quantum gravity, but only in one dimension, what pops out is something amazing, the exact same math that describes standard particle physics. It's a wild way to think about it, but all of particle physics can be seen as just 1D quantum gravity. A cool rhyme for sure, but we're not at the full poem yet.
All right, so if particle physics rhymes with one-dimensional gravity, you can probably see where this is going, right? What happens if we take that rhyme and just extend it? This is the moment we make the leap, the big jump, into string theory itself. This really is the million-dollar question. What if we take those one-dimensional lines from our Feynman diagrams and we just thicken them up a bit? What if the most fundamental things in the universe aren't little points at all, but tiny, vibrating, one-dimensional strings that trace out a two-dimensional surface as they fly through time?
And this one simple change, it changes everything. Look at the comparison. On the left, with particles, you have those sharp, spiky interactions at a single point. But on the right, with strings, the interaction is just a smooth joining of surfaces. It's less like a collision and more like plumbing fitting together. The whole picture just gets smoother, more elegant, no more sharp corners.
Okay, so this whole plumbing picture is nice and pretty, but does it actually do anything useful? Does it solve any real problems? Oh yeah, you bet it does. This one little move from lines to surfaces actually solves two of the deepest, most stubborn problems in all of theoretical physics.
First up, the big one I mentioned, gravity. Our best theory of particles, the Standard Model, is amazing, but it has this one giant glaring hole. It has absolutely no idea how to include gravity. Every time we try to plug gravity into the equations, the whole thing just breaks.
So to get why, you need to know that in the normal particle picture, a force and a particle are two totally different things. A particle is what we call a state. It's the thing at the beginning or end of a line. But a force, like gravity, is an operator. It's something you kind of poke the diagram with in the middle. They're just different mathematical objects.
But this is where the magic of two dimensions comes in. In string theory, that whole distinction just evaporates. Because of a special property of these 2D surfaces, where the physics looks the same no matter how you zoom in or out, pinching the surface to represent a force is mathematically the exact same thing as having a little tube branch off to represent a particle. They're just two different ways of looking at the same geometric shape.
So the bottom line is this. In string theory, particles and forces are the same thing. They're unified. And that means if your theory has strings in it, it must have a particle that acts like the force of gravity, the graviton. Gravity isn't something you add in. It's baked into the framework from the very beginning. It has to be there.
All right, so that's riddle number one. But what about the second great problem? Well, it's the problem of infinities. Whenever physicists tried to calculate quantum gravity the old way, the answers they got weren't just wrong, they were infinite. And in physics, getting infinity as your answer is basically the universe's way of telling you your theory is completely broken.
So where do these infinities come from? They pop up in Feynman diagrams when you have loops of particles that can, for a fleeting moment, all meet at a single zero-sized point in spacetime. And that idea of interacting at zero distance is what makes the math just explode.
But what about in string theory? Well, a loop isn't a bunch of lines anymore. It's a whole 2D surface, like this donut shape, a torus. And here's the beautiful part. A surface like this has a minimum size. It simply cannot shrink down to a single point. It's physically impossible. By getting rid of points, string theory just neatly smooths away the infinities that have been giving physicists headaches for decades.
So, we've seen how this one idea can potentially unite the forces and get rid of those nasty infinities. But all of this is building to what is, without a doubt, the most profound, the most absolutely mind-bending implication of the entire theory.
I want you to just stop and think about how we built this whole idea. We started by imagining a string moving through a background spacetime, right? But as Witten points out here, that spacetime we imagined, it was just the input data. It was the information we fed into the system to define the real physics, which is the 2D theory living on the surface of the string itself. The real action isn't in the spacetime, it's on the string.
This completely flips our entire picture of reality on its head. It means that space-time, the 3 dimensions of space and 1 of time that we live in, isn't the fundamental stage for the universe. Instead, space-time itself is an emergent property. It's something that just sort of crystallizes out of that deeper, more fundamental 2D reality when the conditions are just right. It's not the arena, it's one possible outcome of the game.
And that leaves us with this incredible final question. If the very fabric of space and time isn't the bedrock of reality, if it's just a shadow or a projection from this deeper, stranger world of two-dimensional physics, then what is the real nature of our universe? What is the fundamental stuff? That's the rabbit hole string theory invites us to go down.